Let's look at another application of simple linear equations, the last one on the packet. It says that the total annual health expenditures in the United States were about $28,000 billion in 2012. That's a weird way of writing it. That's the same as 2.8 trillion, whatever. I don't know why I wrote it that way. So anyways, it says which was a 287% increase over the total for 1990. What were the approximate total health expenditures in 1990? So again, first thing is choosing a variable. In this equation, we're asked to figure out what this is. So I would generally call this x, which is we don't know what were the expenditures back in 1990. What I do know is that it has increased to 2.8 trillion in 2012, and I was also told that that is a certain percentage of an increase from its original. And that's those kind of the key information that I need to figure out the original. And so again, I could think about what would an equation look like. Well, what I said in the previous video on percent is that percent increase is equal to the ratio, and I could recopy that formula right here. Percent increase is equal to the ratio in amount of increase divided by the original amount. And in this case, I don't know what the original amount was, that's x, and I don't know what the amount of increase was either. But I could try to translate into this equation where that if I take the original amount and I multiply that into the amount of increase, that would give me the amount of if I take the original amount, multiply it into the percent increase, that would give me the amount of increase in total. So basically, if I do the original amount, which is what I've called x, and I multiply that by the percent increase, which I was also given is 287%. Sorry, I'm a little tired, so I'm slurring a little bit. I will do my best to enunciate. This should give me the amount of increase. And so, cool. But notice that the amount that is in 2012 isn't just the amount of increase, it's the amount of increase, it's the new amount. So if I were to take the original amount and add the amount of increase, this would be equal to 28,000 billion. And so I could write that all out, but I'll just leave it in the units and ignore the billions. And then my answer will maintain the same units that I'm using as I plug my numbers in, which will be in billions. Though I could write this as 2.8, which would then be in trillions. It doesn't really matter as long as I remember that, you know, there's a particular units that I'm using in this equation. So I've kind of written a couple equations, and it's looking like this is getting kind of confusing. But one other thing I could conclude from the second equation is that the amount of increase, if I were to subtract x from both sides, would just be 2800 minus x. So if I plug that in over here, which is often referred to as the substitution property of equations, would be equal to 2800 minus x. Which is just the difference between, right, that's what we did before. The amount that has increased is just the difference between how much is its new value and how much was it originally, which is what I'm choosing x to be. Whoops, I clicked the wrong button. I clicked the wrong button again. Sorry for the technical difficulties. Let me try to return back to where I was. And also, returning back to percentages, remember that percentage, if I'm doing it mathematically in an equation, I would want to convert that back to its decimal form, and I don't usually want to leave it in a percent form. But basically, if I move the decimal place twice to the left, I can convert that back to its numerical value, which would be 2.87. But basically, I have 2.87 times x is equal to 2800 minus x. And there we have an equation. And again, that's kind of the hard part of these, is how would I write an equation that I can solve? And a lot of times we would get stuck just because it's often that we don't necessarily know what certain things like this mean, and that's kind of the point of me going back into it. It's all about knowing a formula, knowing a quantity, knowing what something means. If you do, it's a lot easier to set up an equation from there. And then what I could do is add x to both sides. I could multiply by 100 to get rid of the decimals, but I don't think that that's really necessary. And this would give me 3.87x is equal to 2800. And to finish solving for x, now all I need to do is divide both sides by 3.87. So 2800 divided by 3.87 would give me my initial amount, which is approximately 723.5. And again, that's going to be in billions of dollars, as I said, because the original number I used was in billions. So basically, there we go. And last but not least is, does this answer make sense? So what I'm concluding is that our health expenditures in 1990 were 723 billion, and that now it is 28,000 billion. And so let's make sure it makes sense. So what I'm saying is that if this increased by 287%, it should be to 2,800. And I could check by just multiplying that out. So if I take this answer and if I multiply by 287%, which is 2.87, that will give me this. And remember what I said about percent increase is that once I do that, this is the amount of increase, not the final amount. So if I was to then add it to the original amount, this should give me the new amount. And notice that makes sense. So if I increase this by 287% of the original, that means that I'm increasing it by this amount, which when added to the original gives me 2,800. And so there we go. Again, percent increase is a kind of a confusing quantity. Hopefully I'm not making it worse, and hopefully I'm making it better. But again, I recommend focusing on this formula if you're having trouble, because this is the essence of what percent increase and what percent decrease mean. Anyways, that's it for this week's lecture, well, at least for Friday, for Thursday, I mean. And then we'll have a couple more lectures that will be uploaded soon. A little more review on some basic algebra before class on Tuesday.